We gave an intuitive definition, an idea of the derivative. Section 2.2, well, we gave the formal definition of the derivative, but as we saw in the last several examples, using the definition of the derivative to find the derivative took a long time. It was kind of complicated. So just like in section 1.6, to find the actual limits, if we had the limit rules, limit laws from section 1.7, it turned out to be quite easy. It was a nice, easy technique. And it turns out that in this section, section 2.3 and 2.4 a little bit, that we're going to show, we're going to derive formulas that will simplify our life tremendously so that we can find derivatives quite quickly. And so in this section, that's what we're going to be doing, is proving these laws that will help us to simplify our process of finding derivatives. Okay, so section 2.3, differentiation formulas. So first, let's find the derivative of a constant function. The derivative of a constant function is 0. So if you take the derivative of any constant, you get 0. So derivative of 12 is 0. Derivative of 54 is 0. So let's find the derivative of the function. Well, let f of x equal c. So I'm going to plug in f of x equaling c into the formula, the difference quotient formula for the derivative. So we know that f prime at x is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Replacing every x in the formula, there is none, by x plus h. I get that c is still, well, c. F of x is c. And so the limit as h approaches 0 of f of x plus h minus f of x all divided by h is just limit as h approaches 0 of c minus c over h. Well, c cancels. And so I get the limit as h approaches 0 of 0 over h. Well, 0 divided by h is 0. And so I have here the limit as h approaches 0 of 0. Well, as h goes to 0, 0 remains 0. So this is equal to 0. Therefore, the derivative of any constant is just 0. Any questions about that? Okay. The next theorem. The derivative of x is 1. Let's proceed as before. That f of x equal x. Then f prime at x, limit h approaches 0, f of x plus h minus f of x over h is, wherever I see an x in the formula for f, replace x by x plus h. And so let's just replace this x here by x plus h. Oh, I guess I can't do that. And so I just get x plus h. And f of x is just x. So this is equal to the limit as h approaches 0 of x plus h minus x all divided by h. Well, the x's cancel. So I just get the limit as h approaches 0 of h over h. The h's cancel. So I have the limit as h approaches 0 of 1. But 1 is always just a number 1. So the limit is just 1. Therefore, the derivative of x is 1. Any questions about that? Okay. So I guess I'm going up in powers. So the derivative of x squared is 2x. So I guess I'm tired of writing let f of x equal x squared. So let's use this notation. The derivative of x squared, by definition, is the limit as h approaches 0 of x plus h squared minus x squared, all divided by h. Let's use the special product formula, the perfect square trinomial formula, to simplify x plus h quantity squared. And so x plus h quantity squared is just x squared plus 2xh plus h squared. Therefore, this is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. The x squares cancel. And so this is just equal to the limit as h approaches 0 of 2xh plus h squared divided by h. I can factor an h from each of these terms in the numerator. And so this is just equal to the limit as h approaches 0 of h times the quantity 2x plus h divided by h. The h's cancel. So I just have the limit as h approaches 0 of 2x plus h. Well, as h goes to 0, 2x plus h approaches just 2x. Therefore, the derivative of x squared is 2x. Any questions about that? So far, so good. Okay, let's do this. I guess I'm sick and tired doing it the same way. So let's do the following theorem. The derivative of x cubed is 3x squared. Let f of x equal x cubed. Then for every real number a, the derivative of f at a is equal to the limit as x approaches a of f of x minus f of a divided by x minus a. So this is equal to the limit as x approaches a of x cubed minus a cubed over x minus a. Well, by the special product formula, the difference of cubes formula, x cubed minus a cubed is x minus a times x squared plus ax plus a squared. And so this is equal to the limit as x approaches a of x minus a times the quantity x squared plus ax plus a squared, all divided by x minus a. The x minus a's cancel. And so This is equal to limit as x approaches a of x squared plus ax plus a squared. As x approaches a, well, x squared approaches a squared, ax approaches a squared, and a squared, well, remains at a squared. So there are 3 of these a squares. And so this is equal to 3a squared. This is true for every a, therefore the derivative of x cubed is 3x squared. Any questions about that?
How are you able to get 3a squared from the function above?
You will need to repeat your question because you faded out.
How were you able to get 3a squared from the function above?
Replace every x by a. X is approaching a. So replace each of these x's by a.
Got it. Thank you.
Okay. Now, so I've actually shown that the derivative of f prime at a is 3a squared. But then in this notation, I said, well, if this is equal to, if the derivative is equal to a squared, 3a squared for every a, then for x's, it's also equal to the derivative of x cubed is therefore 3x squared. I don't know, I proved it this way because I was probably tired of, after a while you get tired of doing it the same way. So I use a little bit of variety here. Okay. Well, so now I'm going to prove this in general. So for any power of n, well, for any natural number exponent of n, I'm going to show this. And I'm actually going to do this more than one way. I'm going to do it right now using the binomial theorem. Later, I'll do the same thing. Well, I'll prove the same result using, well, something called the product rule. So using something else, using mathematical induction. So well, of course, you needed to use mathematical induction to prove this, but okay, so let's recall from pre-calculus, well, actually, the first time they show this is in junior high. So not in the same notation, but the first time they show you this is in junior high, the binomial theorem. So let's recall from junior high, I guess, that a plus b to the n is equal to the sum, k equaling 0 to n, of n choose k, a to the n minus k times b to the k, where n here is a whole number. So let's use this result here to prove the power rule. So the power rule is the derivative of x to the n is n times x to the n minus 1. And this is true for any natural number n. It turns out this is actually true for any number. So for any like real number, this will also be a true statement. We won't be able to prove that in this course. We'll only be able to prove it for rational exponents. Certainly for integer exponents, we'll prove it. I think I'll prove it for rational exponents, but I can't prove it for real exponents That will not be until Math 262. So the derivative of x to the n is a limit as x approaches the derivative of x to the n is equal to the limit as h approaches 0 of x plus h to the n minus x to the n all divided by h. So first thing to do here is to rewrite this using this fact. So using this fact here, let's replace this by that. So let's replace these. So I'm going to, so this is equal to the limit as h approaches 0 of, I'm dividing by h. So let me write this as 1 over h out in front, just so that I don't need to divide by this huge quantity by h. So let me just write this 1 over h out in front of this guy. Well, I'm just going to replace, instead of writing a, I'm going to write x. So writing b, I'm going to write h. So x and h here. So just put x here and h here. So this is equal to, there it is, barely. So the sum, k equaling 0 to n, choose k, of replace a here by x. So x to the power n minus k. Replace this b here by h. And so h to the k. Minus, well, this guy. Minus x to the n. So this is equal to limit h approaching 0 of 1 over h times the quantity. Sum k equaling 0 to n, choose k, x to the n minus k, h to the k, minus x to the n. And so this is equal to the limit as h approaches 0 of 1 over h times, let's write out a few of these terms. So I'm just going to write out the first few terms. I really only have, just in case you don't know, don't see what's happening, let's write out the first few terms. And so this will help you at least to visualize what's happening. Again, it's really not necessary to write out these terms. I could have just written out, I could have just gone from here to here because it's obvious. But it's only obvious if you know what's going on. So let me write out the first few terms just in case you don't see. This, just in case you're not fluent in the summation notation. So this is equal to, well, let's plug in k equals 0. N choose 0 is 1. N minus 0 is n. So this is x to the n. H to the 0 is 1. So when k is 0, this first term is just x to the n. Let's look at when k is 1. So this is n choose 1. N choose 1 is just n. Replace k here by 1. So it's x to the power n minus 1. Replace k here by 1. So it's x to the first. H to the first. So this is just h. So when k is 1, this term just becomes n, x to the n minus 1, h. And let me write out, not that you really need to, what happens when k is 2. So this is n choose 2, which is n times n minus 1 divided by 2. Replace k here by 2. So this is x to the n minus 2. Replace k here by 2. So x to the k becomes h squared. Plus, well, all the remaining terms. I wrote out 0, 1, and 2. So the remaining terms go from k equaling 3 to n of n choose k, x to the n minus k, h to the k, minus, well, this last term, x to the n. Any questions on how I wrote out the first 3 terms for that summation? Okay, so note, x to the n's cancel. So I just have this term. So this is, I just have these remaining terms. But notice that I can divide this h, one of these h's. So this cancels here, that becomes 1 less, and this becomes 1 less. So this is equal to, again, limit as h approaches 0 of this first term, n x to the n minus 1, plus these terms, which is I should have wrote k equaling 2. Yeah, that would be a 2 there. Not that it matters. Okay, there. That was a error. Yeah, that's. Because I need this term here, plus these guys. Okay. So, and I can factor out, so I'm factoring out 2 of these. Oh, I'm factoring out 2 of these because that's, okay. Again, not that it matters. Okay, so this is equal to, sorry, I had 2 little errors there with my notation. So this is equal to the limit as h approaches 0 of the quantity n x to the n plus h, because I factored out here, and h from each of these. And so I factor out 1 h here and another h that I put here. So that means that I'm taking away 2 h's. And I start here. I wrote out 0, 1, and 2. I'm actually going to continue with these from the second up to the nth term. So this goes from k equaling 2 to n of, well, same thing, n choose k, x to the n minus k, times h to the k minus 2, because you got rid of 1 to the h's. This thing here is a polynomial involving h's, And when h is 0, this is just going to equal, well, this term here, which is nice and bounded. So this is little o of h. As h goes to 0, this whole term here goes to 0. And so, well, this whole term here goes to 0 as you divide by h. And so, as h goes to 0, that's 0. And so this is just equal to n. And by the way, that's big O. That's big O. That's big O of h. But this goes to 0 as h goes to 0. And so the only thing I have remaining after I take the limit is this term. So this is equal to n, x to the n minus 1. And that's what you wanted to show. Any questions about this? A lot of times what usually the way that you see this proof is where they just sort of say plus dot, dot, dot. So they don't actually need to write out. They don't write out what the other terms are, but you should at least see what the terms are. So we could also prove the power rule by factoring. So I'm going to do this sort of factoring because it's sort of easy to see. So let f of x equal x to the n. Then f prime at a is a limit as x approaches a of x to the n minus a to the n over x minus a. This is equal to limit as x approaches a of x minus a times x to the n minus 1 plus a x to the n minus 2 plus a squared x to the n minus 3, etc. So you see what's happening. These a's here are rising in powers, and these x's here are dropping in power. So plus, well, dot, 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 a to the n minus 1. The x to the n, x minus a's cancel. And so you just have this term. So let me write, so even though I didn't write it as a summation here, let me write as a summation here, just so that you can see what it is actually equal to. So this is the limit as x approaches a of the sum, k equaling 0 to n minus 1, of x to the power n minus 1 minus k times a to the k. As x approaches a, let's replace these x's by a. This is just, well, the a to the k's cancel. So this approaches a. So this is an a to the k. So these cancel. So I just get x to the n minus 1, or a to the n minus 1. And how many do I have? Well, they go from 0 to n minus 1. That's n of them. So there are n of these a to the n minus 1s. Therefore, x to the n, the derivative of x to the n is n times x to the n minus 1. So this is yet another derivation of the power rule. Any questions about that? Any questions on that derivation? Okay, so I've given you two different ways to prove the power rule. We'll also prove it by mathematical induction later in this section. So it turns out that the derivative is a linear transformation, because I told you the derivative was a linear transformation. So let me show you that. Theorem, the constant multiple rule. let f of x be differentiable, let c be a real number, then c times f of x is differentiable, and the derivative of c times f of x is c times the derivative of f of x. Let's prove that. The derivative of c times f at x is, by the difference quotient definition, the limit as h approaches 0 of cf at x plus h minus cf at x divided by h. Well, by definition, the pointwise definition of scalar multiplication, this is equal to the limit as h approaches 0 of c f of x plus h minus c f of x all divided by h. I can factor out what's in common, c, and bring it out in front of the limit by the limit properties from section 1.7. So this is equal to c as the limit as h approaches 0, f of x plus h minus f of x all divided by h. But this is just the derivative. And so this is equal to c times f prime at x. Now, this limit exists because f is differentiable. Any questions about that? So to take the derivative of some constant times a function, it's just equal to the constant times the derivative of the function. Okay. The sum rule. Let f be differentiable and let g be differentiable. Then f plus g is differentiable. And the derivative of f plus g is the sum of the derivatives of f and the derivative of g. So f of x plus g of x prime is equal to f prime at x plus g prime at x. So let's show this. So f of x plus g of x quantity prime is a limit as h approaches 0 of f x plus h evaluated x plus h minus f plus g at h at x. Oh, try that over again. The limit as h approaches 0 of x plus g at x plus h minus f plus g at x all divided by h is equal to, using the pointwise definition for the sum of two functions, this is equal to, and distributing the minus sign inside, this is equal to the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x minus g of x all divided by h, which is equal to, well, let's group this and group this together. Then this is equal to the limit as h approaches 0 of f of x minus, the limit as h approaches 0 of f of x plus h minus f of x all divided by h, plus the limit as h approaches 0 of g of x plus h minus g of x all divided by h. Please note that in order for this to be true, both of these limits, each of these limits here had to exist. And they do because f and g are both differentiable. So this statement here would not be a true statement unless I assumed that f and g were differentiable. Because it may not be equal if that limit doesn't exist. Well, this is just f prime at x plus, and this is g prime at x. So this is equal to f prime of x plus g prime of x. And that's what I wanted to show. So this combined with this says that the derivative is a linear transformation. Any questions about this? Okay, so since I'm getting tired of using the same definition of derivative, and actually this no, just because I'm tired of using the same definition of derivative, I'm going to use the definition of derivative that we had involving linear transformations. It's from Loomis and Steinberg, the Loomis and Steinberg definition. If f is differentiable, then delta f sub x at h is equal to d f sub x at h plus little o of h. Well, rewriting this in common notation, this is just f of x plus h minus f of x, and rewriting this. And this linear transformation, since the linear transformation goes from reals to reals, then I'll look at its matrix representation. Its matrix representation is just a 1-by-1 matrix. I will associate with this 1-by-1 matrix the entry of the 1-by-1 matrix. And so doing this isomorphism, I can rewrite this in the usual notation. F prime of x times h plus little o of h. Adding f of x to bring this f of x to the other side of my equation, I have that f of x plus h is equal to f of x plus f prime of x times h plus little o of h. And so I'm going to use this as my definition of the derivative. So f is differentiable if there exists this function so that this holds. So let's use that to prove linearity, that a differentiable, that the derivative operator is a linear transformation. So I want to show that that the function d, the operator d, from the vector spaces R into the vector space R, defined as the derivative. I want to show that this is a linear transformation. And so, theorem, linearity. Let f be differentiable and let g be differentiable, then, and this is true for any real numbers a and b, af plus bg prime at x is equal to a f prime at x plus b g prime at x. Oh, why isn't that have it in parentheses? Okay. So let's do this. First off, since f is differentiable, then there exists a function f prime of x such that f of x plus h is equal to f of x plus f prime of x times h plus little o of h. Since g is differentiable, then there exists a function g prime of x such that the following holds: g x plus h equals g of x plus g prime of x times h plus little o of h. So let's look at this. And so a f plus bg at x plus h is equal to, well, by the pointwise definition of addition and scalar multiplication, this is equal to a f of x plus h plus b g of x plus h. Well, I know what f of x plus h is and g of x plus h. So this is equal to a times the quantity f of x plus f prime of x times h plus little o of h plus b times g of x plus times the quantity g of x plus g prime of x times h plus little o of h. And so that we multiply a inside the parentheses, b inside the parentheses. So this is a times f of x plus b times g of x plus a times f prime of x times h plus b times g prime of x at h plus a constant times little o of h plus another constant times little o of h is equal to little o of h. Let me rewrite this first term in terms of, well, its definition, the pointwise definition of addition. This is equal to AF plus BG at X plus, again, using the pointwise definition of addition and scalar multiplication, plus AF prime plus BG prime at X times H plus little o of H. But now, recall, if you have something evaluated at X plus H, which is equal to that same thing evaluated at X plus something times H, something not involving H times H plus a little o of H, then that's something that doesn't involve H is your derivative of that original function. So we had that this guy evaluated X plus H is equal to the same thing evaluated at X plus something not involving H times H plus a little o of H. So this something that does not involve H is defined as your derivative. Therefore, AF plus BG quantity prime is AF prime plus BG prime. Any questions about that? So this is really the first time that you've seen me use this other definition. This definition from Loomis-Steinberg in a proof. Any questions about this? Okay. This result shows that the derivative is a linear transformation. Let's do the following theorem. Wait 1 second. So, the difference rule. Let f be differentiable, and let g be differentiable. Then f minus g prime at x is equal to f prime at x minus g prime at x. Okay, so let's do this. Well, when we showed the sum rule, I used the difference quotient. So the proof would be the same. So I'm going to give you the proof involving this definition from Loomis-Steinberg. F of x plus h is equal to f of x plus f prime of x times h plus little o of h, since f is differentiable. Since g is differentiable, g of x plus h is equal to g of x plus g prime of x times h plus little o of h. Therefore, f minus g at x plus h is equal to f of x plus h minus g of x plus h. But we know what f of x plus h is, and we know what g of x plus h is. So this is equal to f of x plus f of x plus g prime of x times h plus little o of h minus g of x plus g prime of x times h plus little o of h. Let me just regroup things. So I have, this is equal to f of x minus g of x plus, I don't know, right, plus, there it is. There, plus f prime of x at h minus g prime of x at h plus, well, little o minus little o is little o. So plus little o of h. Again, using the notation, the pointwise notation for the difference of functions, this is equal to f minus g at x plus f prime minus g prime of x at h plus little o of h. Therefore, that's my derivative. And so I have that f minus g prime is f prime minus g prime. And that's what I wanted to show. Yeah. The product rule. Let f be differentiable. Let g be differentiable. Then f of x times g of x prime is equal to f prime at x times g of x plus f of x times g prime of x. This is also called Leibniz rule. So one of the inventors of calculus, Leibniz. Hopefully I'm spelling his name correctly. So this is the Leibniz rule, named after Gottfried Leibniz, who independently also derives calculus. Newton derived calculus probably 30 years before Leibniz did, but Leibniz published. So Newton did not publish his results for like 40, 50 years after he actually derived calculus. So Leibniz was actually the person who first published the results. And then Newton afterwards published his results. So they're given joint inventors of calculus because Leibniz was independent. He had not seen the work, no one had seen the work of Newton, even though people thought maybe he might, because he was able to do a whole bunch of things and they didn't know exactly how he was able to do them. And then it became evident after he published his results that the reason he was able to do it is because he knew the results from calculus. He had invented it. Okay, so Leibniz. So this is called Leibniz rule. And strangely enough, when Leibniz actually did this, actually his results were wrong. So he actually didn't give this. He actually gave a incorrect formula for the derivative. He thought, I think if I remember, he thought that f times g prime is just f prime times g prime. And so this is the correct result. So even though he gave the wrong result, he published it first. And so it's still given his name. So we call it either the product rule, but I'll usually call it Leibniz rule. Okay, so let's do this. It's actually easier to prove Leibniz rule using the Lorentzen-Steinberg notation than doing the difference quotient. So I think I'm going to be doing, yes, I will be doing. So I'll do this as follows. So since f is differentiable, then there's just the f prime such that f of x plus h is equal to f of x plus f prime of x times h plus little o of h. Since g is differentiable, then there exists a function g prime of x such that g of x plus h is equal to g of x plus g prime of x times h plus little o of h. So let's look at f times g evaluated x plus h. Well, f times g evaluated x plus h by the pointwise definition is equal to f of x plus h times g of x plus h. And we know each of these. So this is equal to, well, the product of these. So this is equal to f of x, the quantity, f of x plus g prime, I'll start that over again. So this is equal to the quantity, f of x plus f prime of x times h plus little o of h times the quantity, g of x plus g prime of x times h plus little o of h. And now let's just multiply. So let's multiply this out. So let's multiply. So I have that this is equal to f of x times g of x plus f of x times g prime of x times h. And so that's this term. So f of x times g prime of x at h plus f of x times little o of h, which is little o of h. And now let's multiply this. And so if I do that, well, I have f prime of x times h times g of x, which is here. So f prime of x times g of x times h. Now let's multiply this times this. But I have an h here times h, which makes this an h squared. So f prime of x times h times g prime of x times h becomes something involving h squared, which is little o of h. So this becomes little o of h. F prime of h times little o of h is certainly little o of h. Little o of h times anything is, well, little o of h. So I get that this is equal to f prime, I'm sorry, this is equal to f of x times g of x plus f prime of x times g of x times h plus f of x times g prime of x at h plus little o of h. Let me factor out an h here. So this is equal to f of x times g of x plus the quantity f prime of x times g of x plus f of x times g prime of x all times h plus little o of h. But by definition, that means that the derivative of this is equal to that. So this is equal to, so this says that the derivative of f prime, so the derivative of f times g is f prime times g plus f times g prime. And this is my product rule. Any questions about that? And so that's Leibniz rule. Okay. Theorem. Let f be differentiable and let g be differentiable and let x be in the domain of f intersect the domain of g, take away the kernel of g. You don't want to divide by 0. Then f divided by g is differentiable, and the derivative of the quotient f divided by g at x is f prime at x times g of x minus f at x times g prime, all divided by g squared. So the derivative is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So the derivative of a numerator divided by a denominator is the derivative of the numerator times the derivative times the denominator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So let's prove this using what we just did for the product rule. Let h equal f over g. Then, multiplying both sides of my equation by g, f is equal to gh. And so by the product rule, we have the following, that f prime of x is equal to g times h prime at x, which is equal to f prime, blah, blah, which is equal to, we're doing g's and h's, which is equal to g prime of x times h of x plus g at x times h prime of x. Let's multiply both sides of my equation by g of x. So I have that f prime of x. So I have that f prime times g is equal to g prime times g times h plus g squared over times h prime. Okay, so I have that since g times h is f, I have that f prime times g is equal to g prime times f plus g squared h prime. Therefore, solving for h prime, I have that h prime is equal to f prime times g minus, bring this over, g prime times f, all divided by g squared. So remember that h is f over g. Therefore, f divided by g, quantity prime, is f prime times g minus f times g prime, all divided by g squared. And that is what you wanted to prove. Any questions about that? So I just used the fact that I already had proven things about the product rule. And I use that to show you, to derive the quotient rule. So let's look at the power rule yet again. The derivative of x to the r is r times x to the r minus 1. And this is true for all r that are real numbers. So for every real number r, this is actually holds. Now, this will be proven in calculus 2. So in Math 262, they'll actually show this. But let's revisit my proof of the power rule using Leibniz rule. So I want to show the following. The derivative of x to the n is n times x to the n minus 1, and that this is true for any natural number n. So I'm going to prove this using mathematical induction. If you recall, mathematical induction was similar to having a whole bunch of dominoes, where if the first domino fell and one domino falling causes the next domino to fall, then all dominoes will fall. And so I want to show first that the first domino falls. Then I want to show that if a domino falls, then the next domino falls. That will then show that all dominoes fell. Okay, so let's do the initial case. When n here is equal to 1. So I want to look at x to the first power, the derivative of x to the first power. So this is just the derivative of x. Well, we already have proven that the derivative of x is equal to 1. And so, well, 1 is the same as 1 times x to the 0. So this is equal to 1 times x to the 1 minus 1. So this case holds when n here is equal to 1. So I've shown my initial case. Now let's show the induction case. So I've shown that the first domino fell. Now I want to show that if a domino falls, the next domino will fall. So let's suppose that the domino falls. So suppose that x to the n, suppose that the derivative of x to the k is k times x to the k minus 1. Then let's look at the next domino, the derivative of x to the k plus 1. And let's see if this formula here has the same formula as this. So let's write x to the k plus 1 as x to the k times x. So using the properties of exponents, let's just rewrite x to the k plus 1 as x to the k times x. By Leibniz rule, the product rule, the derivative of x to the k times x is, well, the derivative of x to the k times x. plus x to the k times the derivative of x. The derivative of x to the k, by our induction hypothesis, is just equal to k x to the k minus 1 times, well, x plus x to the k times the derivative of x. The derivative of x is 1. And so multiplying x to the k minus 1 times k times x, I just get that this is equal to x to the k. So I have a k times x to the k plus x to the k. I can factor out x to the k. And so this is equal to x to the k times k plus 1. And let's rewrite this as k plus 1 times x to the k. And let's rewrite k as k plus 1 minus 1. The ones cancel. And so this is equal to k plus 1 times the quantity times x to the k to the power k plus 1 minus 1. But this has the exact same form as this if I replace k here by k plus 1. Therefore, the next domino fell. And so, by the principle of mathematical induction, the derivative of x to the k is, of derivative of x to the n is n times x to the n minus 1. And we've shown that this is true for every natural number n. So I'm done. Any questions about this? Actually, I think this is the easiest of the proofs. So of the proofs of the power rule, this I think is easiest. It doesn't involve these big calculations of either trying to factor or trying to use the binomial expansion. Oh, okay, so now let's do some examples. So now that we have all of these techniques, all these theorems under our belt, finding derivatives should be easy. So rather than using the limits and all that, we'll just use the rules. Okay, so let's take the derivative. So let's use the power. So let's see. Let's use the power rule. Actually, I should put it in. Let's not put it in this color. Let's put it in a different color. And you'll figure out why in a second. Okay, so let's do the power rule. So power rule says that the derivative of x to the n is n times x to the n minus 1. Therefore, the derivative of pi squared is 2 pi to the 2 minus 1, which is 2 pi. What did I do wrong? Why am I writing garbage? What is wrong? Remember, whenever you use formulas, you must rewrite everything exactly in terms of the assumptions of exactly the same form so that you can use the rule. If not, you'll do things wrong. Why is the derivative of pi squared not 2 pi? Why is this? Why would I take off all points for this? Right? I wouldn't even give you any points for this. What is completely wrong here? Okay, let me ask you something else. What's the derivative of 5?
0.
Okay, what's the derivative of 12?
Would it not work because like pi is like
Well, what's the derivative of 12?
a 0? Would it be 0?
What? Why?
Is it because pi is like not a variable and it's just like 3.14?
It's a constant. It's a number.
Yeah.
Pi is a number. What's your derivative of a number? 0. Why? And that's why I took off all points, because everything you've written here is garbage. Well, everything I've written here is garbage. So, well, this is garbage. Let me go back and correct this. So, recall that the derivative, now I put it in black so that you know that it's correct. Okay, so, oh, come on. Because the derivative constant is 0, we have that the derivative of pi squared is 0. Just because I wrote it strangely doesn't mean it's not a constant. Pi squared is a constant, a fine constant, just like 12 is a fine constant. It's perfectly nice. And it's not a variable. There's no x's there. Therefore, the derivative of this constant is 0. Any questions about that? Okay. Yeah. So unfortunately, so all of these rules are nice and fine, but be careful. So I guess practice. And this, of course, I did it on purpose to see it, because a lot of times people do that accidentally. So let's take the derivative of this. I'm going to use the constant multiple rule. So derivative of c times y to the negative 6 is, well, the constant c, times, bring down the exponent on front, negative 6. Subtract 1 from the exponent, negative 7. And you're done. So the derivative of cy to the negative 6 is a negative 6cy to negative 7. Any questions about that? Okay. Let's do problem number 16. Four pi is a constant. So the derivative of 4 pi r squared is just 4 pi. Times the derivative of r squared, bring down the constant out front. Subtract 1 from the exponent. 2 times 4 is 8. So this is 8 pi. 2 minus 1 is 1. So this is r. And so the derivative of 4 pi r squared is 8 pi r. Any questions about that? Okay. Let me do problem number 22. The derivative of 1 plus 16t squared over 4t cubed, quantity cubed. Well, I don't know how to take the derivative of that because I have a parentheses. So you must rewrite, in order to use a formula, it has to be in the exact form in order of the, well, formula for you to use it. So you can't deviate from the form in the formula if you do, then you won't be able to use the formula. And so let's rewrite this as 1 plus 16t squared over 4 cubed, 64t cubed. Now, I can simplify. I can use the quotient rule on this, but I'm lazy. Whoa. So in general, before you take so let me tell you a rule. It's really something that well, it's not really a rule. It's if you want to save headaches and save yourself time, remember, simplify before you take the derivative. You do not need to simplify after you take the derivative. So what I notice students doing is they do the opposite. What they do is they don't simplify, they take the derivative, and then they try to simplify the derivative. Before you take the derivative, always simplify first. Then, after you've taken the derivative, you can leave it in the unsimplified form unless you want to do something with the derivative, such as taking the second derivative or setting the first derivative to 0 or doing something else. But if you're just taking the derivative and you're not doing anything after that, there's no need to simplify. So simplify before differentiating. You don't need to simplify afterward. So notice I'm dividing each of these by 64t cubed. So this is equal to 1 over 64 times 1 over t cubed, t to the negative 3. Plus 16 divided by 64, which is 1/4, times t squared divided by t cubed, t to the negative 1. And now let's differentiate. Remember that a derivative is linear. So I'll bring down the negative 3 out in front. Subtract 1 from the exponent. Bring the negative 1 out in front. Subtract 1 from the exponent. And you're done. Any questions about that? Notice that if you didn't, there actually is a way, but you don't know yet, to differentiate this using what's something called the chain rule, the general power rule. And you could actually take the derivative without simplifying, but it'd be so much more difficult. Recall that the quotient rule actually is fairly difficult. So if you simplify first, I mean, this is actually taking the derivative of this was actually quite easy. Okay, so any questions about that? So I guess I should really just write this down. Simplify before taking derivative. Usually, you do not need to simplify. After taking the derivative. So you should really commit this to memory. This will help you a lot. So simplify before taking the derivative. Usually you do not need to simplify after taking the derivative. So that's the rule of thumb, basically. Okay. let me do problem number 26. So, in problems 25 through 44, differentiate. I want to find the derivative of the quantity u cubed plus 1 times the quantity 2u squared minus 4u minus 1. So I'll just use the product rule. Derivative of the first times the second plus the first times the derivative of the second. And you are done. So you take the derivative of the first times the second plus the first times the derivative of the second. Any questions about that? Okay. So let me do problem 42. A times t over bt squared plus ct cubed. What's the first thing I should do?
Simplify it.
Simplify first. So let's simplify first. Factor out a t. So the t's cancel. Okay, so this is equal to. Oh, I see. Oops. Where did that come from? Okay. So this is equal to A over BT plus CT squared. Let me do that. So this is equal to A BT plus CT squared. I'm going to show you something in the future. Let me show you something from the future. Not that far into the future, just like probably, actually it might be tomorrow, but might be today. So just a few minutes into the future, 15 minutes in the future. So let me tell you the general power rule. So even though I have not proven the general power rule yet, I will prove the general power rule either later today or sometime tomorrow, at the beginning of class tomorrow. So the derivative of f of x to the n, where f here is a differentiable function, is n times f of x to the n minus 1 times f prime of x. So let me use that fact to differentiate this. So f prime of t is therefore equal to, well, I have a constant here, so let's leave that constant out in front by the constant multiple rule. The general power rule says that to differentiate some function to a power, you just bring that exponent out in front, minus 1, and subtract 1 from the exponent. So let's bring the negative 1 out in front. Rewrite what's in the parentheses, BT plus CT squared, all to the power of 1 less. -1 minus 1 is -2. All times the derivative of what's inside. So let's take the derivative of what's inside. So the derivative of BT is B. The derivative of CT squared is 2CT. And I am done. Any
Yes, sir.
questions about that?
Which rule did you use
Question.
to differentiate the second part
Oh,
for the B
this is
plus
just
2CT?
let's take the derivative.
Oh, no, I understand. But so you used first the power rule to bring the exponent down. What was the reason for you to also differentiate what was inside?
That's what's called the general power rule.
Got it.
So
Okay,
that's why it's
thank you.
called the general power rule.
Got it.
So the general power rule is that you basically take the derivative of what's inside, evaluate at what's inside, and then multiply by the derivative of what's inside.
Got
And
it.
that's
Got
called
it.
the general power. So it's something we haven't seen yet, but we will see probably still today, even though we only have like half an hour. We'll see that today. That's in the next section, I believe, which is
Thank
something
you.
called the chain rule. And so we'll see that. But I think it's sort of, in this case, it's nicer to use the general power rule than the quotient rule. So I wanted to show that to you anyway. Okay, so any other questions about this? So I gave you something in the future to do this. Okay. In problems 55 through 58, find equations of the tangent line and the normal line to the curve at the given point. So problem 58, y equals the square root of x over x plus 1, evaluated at 4, comma, 0.4. Okay, so first off, suppose I have some function. And this is its tangent line. The best linear approximation to the function at x equal a. The normal line is the line perpendicular to it, to the tangent line. So the normal line is just perpendicular to the tangent line. So they're asking you to find both the tangent line, we know how to do that, and then the normal line, which just says, well, take the line perpendicular to it, passing through that same point. And you know how to find the perpendicular. Once you know the slope of a line, defined as perpendicular, the slope of a line perpendicular to it, just take its negative reciprocal of the slope. Okay, so that's not so bad. It looked worse than what it was, but now that we know the definition of normal, then it's not so bad. So I have here y is equal to, let's write the square root as x to the 1/2 over x plus 1. In general, so if you have something like the cube root, I don't know how to differentiate that, so rewrite it in a form that you do know how to differentiate. Oh, we don't know how to differentiate x to the 1/2 because I haven't shown you. But I told you that you could differentiate x to the 1/2. Oh, If they give us problem we can't do, but that's fine. I told you that you could differentiate, you could use the power rule, even though we only showed the power rule for whole number exponents, it still works for any real number exponent. So I guess even though we don't prove it, we assume that the things like the power rule are so obvious that you don't even notice that we haven't proven it for other exponents. Okay, so similarly, if you wanted to take the absolute value of the derivative of the absolute value of x, you would have to write it as the square root of x squared and then differentiate that. Okay, so in general, if there are things that you don't know how to differentiate, maybe you can rewrite it in terms of things that you do know how to differentiate. So now let's take the derivative. I'm going to take the derivative of this guy using the quotient rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And so let's simplify this. I don't like a fraction. So actually, let me multiply by 2 rad x. Yeah, let's multiply and divide by 2 rad x. So the 2 and the rad x's are going to cancel because this is divided by 2, so that cancels. This is divided by x to the 1/2, so the square root of x's cancel. So these cancel. So all that remains is x plus 1 in the numerator. Next, well, 2 times -1 is a -2. X to the 1/2 times x to the 1/2 is just x. Over, well, 2 rad x, x plus 1 squared. So this is equal to 1. X minus 2x is just minus x over 2 rad x, 1 plus x squared. Okay. Good. Now we want to find the slope of the tangent line when x is 4. Yes, when x is 4. So let's plug in 4. So 1 minus 4 over 2 rad 4, 1 plus 4 squared. 1 minus 4 is a -3. 2 times square root of 2 is, well, 2 times 2 is 4. 5 plus 4 plus 1 is 5. And so that's just going to be 25. So this is a -3 over 100. They write that in decimal. I don't know. I don't want to write decimals. Okay, so I'll just leave it as -3 over 100. So now we call the point slope form for the equation of a line. Y minus y1 equals mx minus x1. So let's find the equation of the tangent line. Y minus y1, which is 0.4, which is 4 over 10. Maybe I'll write it as 2/5 is equal to the slope. Maybe I will write this a little further down. Oh, that's great. Oops. And so this is equal to the slope, which is negative 3 over 100 times x minus, I believe, 4. Yeah, x1 is 4. That is the equation of the tangent line. So now let's find the equation of the normal line. So the equation of my normal line, it goes through the same point. So it's still y minus 2/5. And it's still x minus 4. Now, the only difference is that recall that the slope of your tangent line is the negative reciprocal of the slope of your original line. So let's take the negative. So this negative becomes a positive. And take the reciprocal of 3 over 100, which is 100 over 3. And that is the equation of your normal